सोचो, एक सितारा जो लाखों सालों तक चमक रहा था एकदम से इतनी जोर से फट जाए कि पूरी गैलेक्सी हिला दे। हाँ दोस्तों, हम बात कर रहे हैं सुपरनोवा की, यूनिवर्स के सबसे जबरदस्त धमाके जो नए तारे और प्लैनेट्स जन्म देते हैं। Imagine, if you will, a star, ablaze for millions, even billions of years, suddenly erupting with such ferocity that its light briefly outshines an entire galaxy. These are supernovae, my friends, the grandest fireworks displays in the cosmos. Cosmic engines that forge the elements for new stars, new planets, and even life itself. ये वीडियो पूरी तरह AI generated है, तो हर एक सीन को मेज से देखो और फैक्टफुल को सब्सक्राइब करना मत भूलना। Imagine a star much more massive than our own sun, reaching the end of its life. It's like a cosmic pressure cooker, where the star has been fusing hydrogen into helium for eons, generating the energy that makes it shine. But eventually, the fuel runs out, and the outward pressure from the nuclear reactions can no longer hold back the immense gravity of the star's core. The core collapses in on itself with unimaginable force, creating a shockwave that travels outward at nearly the speed of light. This shockwave is so powerful that it rips the star apart in a cataclysmic explosion, a supernova. Now, a supernova isn't just any explosion. It's a cosmic spectacle, a burst of light so bright that it can outshine an entire galaxy for weeks or even months. For a brief, shining moment, a single star becomes visible across billions of light years, a beacon in the vastness of space. That's the power of a supernova. Let's delve deeper into the life cycle of these massive stars. Those behemoths at least 8 times the mass of our sun. For millions of years, they live fast and die young, their immense gravity driving intense nuclear fusion in their cores. Hydrogen fuses into helium, generating the energy that makes them shine so brightly. But this process can't last forever. Eventually, the star's core begins to run low on hydrogen. The outward pressure from fusion weakens, and gravity, always hungry, starts to gain the upper hand. The core contracts, heats up even further, and begins to fuse helium into heavier elements like carbon, oxygen, and neon. This fusion of heavier elements provides a temporary reprieve, but it's a losing battle against the relentless pull of gravity. The core continues to contract and heat up, forging even heavier elements like silicon, sulfur, and iron. Iron, however, is the end of the line. With no more fuel to burn, the core can no longer support itself against the crushing weight of the star's outer layers. The collapse of a massive star's core is a violent event. Imagine the sun, 333,000 times heavier than Earth, squeezed into a tiny sphere. That's the density of a collapsing stellar core. The pressure is trillions of times greater than the ocean's deepest point. Protons and electrons form neutrons, releasing neutrinos into space. The dense neutron core resists compression, causing a cataclysmic collision. A shockwave propagates outward at nearly the speed of light. This rips the star apart, blasting its outer layers into space. The energy released is mind-boggling. A supernova can outshine an entire galaxy, radiating immense energy. The after effects of a supernova are as profound as the explosion itself. Imagine this, the shockwave from the explosion expanding outward, compressing nearby clouds of gas and dust. This compression can trigger the formation of new stars, igniting the fires of creation in the wake of destruction. But it's not just new stars that supernovae help create. Remember those heavy elements forged in the heart of the explosion. As the supernova remnant expands and cools, these elements mix with the surrounding interstellar medium. This enriched material becomes the raw material for new planets, planets that will form around newly born stars. Think about that for a moment. The iron in your blood, the calcium in your bones, the gold in your jewelry. All these elements were created billions of years ago in the heart of a dying star. We are quite literally stardust. Now, not all supernovae are created equal. Some arise from single stars collapsing under their own weight, as we've discussed. But others, known as Type 1 as supernovae, have a more dramatic origin story. They involve a stellar tango, a dance of death between 2 stars locked in a gravitational embrace. Imagine a binary star system, 2 stars orbiting a common center of mass. One of these stars has reached the end of its life and evolved into a white dwarf, a dense, Earth-sized ember left behind after a star like our sun exhausts its nuclear fuel. The other star is often a red giant, a star in its twilight years that has swollen to many times its original size. Now the white dwarf, though small, is incredibly dense and possesses immense gravity. This gravity acts like a cosmic vacuum cleaner, pulling material, primarily hydrogen and helium, from its companion red giant star. We've explored the fiery demise of white dwarfs in Type 1, a supernovae. But what about those massive stars? Those cosmic giants that live fast and die young? Their end comes in the form of a Type 2 supernova, a spectacular collapse brought on by the relentless crush of gravity. Picture a star at least 8 times more massive than our Sun. Its core a raging inferno of nuclear fusion. It has been forging heavier and heavier elements, from helium to carbon, oxygen, and all the way to iron. But iron, as we've learned, is a cosmic dead end. With no more fuel to burn and no more energy to generate, the core can no longer support itself against the immense gravitational pressure. In a heartbeat, the core collapses, imploding in on itself with unimaginable force. This implosion sends a shockwave rippling outward through the star. This shockwave, traveling at nearly the speed of light, tears through the star's outer layers, blasting them into space in a brilliant explosion. It might seem strange to think about it, but those distant explosive events, those supernovae, are intimately connected to our very existence. They are, in a very real sense, the reason we are here today. Remember those heavy elements forged in the hearts of dying stars? As supernovae remnants expand and cool, those elements, carbon, oxygen, nitrogen, iron and more, mix with the surrounding interstellar gas and dust. This enriched material becomes the raw material for new stars and planetary systems. Our own solar system, including our planet and everything on it, formed from such a cloud of enriched interstellar gas and dust billions of years ago. The iron in your blood, the calcium in your bones, the oxygen you breathe, all these elements were created in the fiery furnaces of long-dead stars. We are, quite literally, stardust. The atoms that make up our bodies were once part of stars that lived and died long before our sun even formed. It's a humbling and awe-inspiring thought. Supernovae also play a vital role in driving the evolution of galaxies. Let's travel back to 1054 AD. Imagine a new star, brighter than Venus, visible even during the day. This supernova, recorded by Chinese astronomers, shone for almost 2 years. Occurring 6,500 light-years away in Taurus, it's known as SN 1054. The star's death was a spectacular explosion. Its remnants formed the Crab Nebula, a glowing testament to a supernova's power. At its heart lies a pulsar, a rapidly rotating neutron star. Fast forward now to the year 1987. On February 23rd, astronomers witnessed a supernova that occurred in a neighboring galaxy, the Large Magellanic Cloud, a mere 168,000 light-years away. This supernova, dubbed SN 1987A, was the closest and brightest supernova observed since the invention of the telescope. SN 1987A was a watershed moment for astronomy. For the first time, scientists were able to study a supernova in detail with modern instruments, observing the evolution of the explosion across the electromagnetic spectrum, from radio waves to gamma rays. One of the most important discoveries from SN 1987A was the detection of neutrinos. Remember those ghostly particles released during the core collapse of a massive star? Scientists had predicted that a supernova should release a burst of neutrinos, and SN 1987A provided the first direct confirmation of this theory. Observations of SN 1987A also provided insights into the processes that create heavy elements in supernovae. We've explored the power of supernovae, but the universe, as always, has even more extreme events up its sleeve. Enter hypernovae, the most luminous explosions known, dwarfing even the most powerful supernovae. Imagine a star not just 8 times more massive than our Sun, but hundreds of times more massive. These stellar behemoths are incredibly rare, but when they die, they go out with a bang that makes a supernova look like a firecracker. Hypernovae are thought to occur when these supermassive stars collapse at the end of their lives. But instead of a simple explosion, the collapse can trigger a runaway thermonuclear reaction that rips the star apart in a cataclysmic blast. The energy released in a hypernova is almost incomprehensible. It's estimated that a single hypernova can outshine an entire galaxy for a brief period, releasing more energy in a few seconds than our Sun will emit in its entire 10 billion year lifespan. तो दोस्तन, आपने देखा कैसे एक सितारा जब मरता है तो नए तारे और प्लैनेट्स जन्म लेते हैं। सुपरनोवा सिर्फ डिस्ट्रक्शन नहीं, बल्कि नए जीवन की शुरुआत भी है। We've journeyed together to the hearts of dying stars, witnessed the awe-inspiring power of supernovae, and learned how these cosmic explosions forge the elements that make up our world and ourselves. We are, each and every one of us, products of this grand cosmic cycle. अगर वीडियो पसंद आया तो लाइक करो और नए तरीकों के बारे में जानने के लिए फैक्ट फ्यूल को सब्सक्राइब कर लो।